get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. We're in the middle of examples last time, so let us get into it. Okay, there we go. Boom, boom, boom. Have these two guys to finish up. People still trickling in here. Let's let them in. And yeah, let's finish these guys up. I don't even know how much space am I going to need here. Okay, let's finish that up. And I don't know why that's not fully typed. Hold on. Okay, fixed. All right. So we were talking about implicit differentiation last time, and we looked at a very intuitive way to go about doing this, especially if you have two variables, y and x. You know that x is the independent variable. You go through, you differentiate as usual, apply all your derivative rules, except whenever you differentiate a y term, you multiply by y prime. And then at the end of the day, you solve for the y prime, and that's how you get it. You can generalize this rule by simply just saying, whenever I differentiate a dependent variable, I multiply by the prime of that dependent variable. Whenever I differentiate by the independent variable, I don't do anything, right? It just applies the rules as usual. So let's actually go through and do these guys. Find y prime dy dx. If you know that e to the x plus y squared plus ln of x plus y equals 3. Okay, go. What do we do here? How do I differentiate the e to the x plus y squared? I don't know if it's me or you, but
my AirPods, sorry. So
oh yes,
e
I can hear you good now. Yeah.
to x plus y squared times x plus y squared prime, like.
So you want e to the x plus y squared times x plus y squared prime?
Yeah.
Yeah, but what is that? What is the derivative of x plus y squared?
Yeah, so is 2y prime.
I mean, well, the derivative of y squared is 2y prime, 2y y prime, yeah.
Yeah, so it's 1 plus 2.
Right. So you differentiate the x, you get 1. Differentiate the y squared, you get 2y y prime. Because you differentiate a y term, you have to multiply by the prime. Right, so that's the derivative. Remember, derivative of e to something is the derivative of the power times the original function. Okay, plus, all right, how do we differentiate the ln of x plus y?
So 1 plus y prime over x plus y.
So it's the derivative of the inside over the inside, right? Derivative of x is 1, derivative of y is y prime. All right, equals, well, 0, right? Derivative of 3 is 0. So that's it. The calculus is done. What we need to do now is we need to isolate the y prime. That's the guy we want. How do we do that?
Could you just factor it out?
Factor it out? How?
Oh wait, no, because there's the e plus y squared if you distribute
So maybe you want to distribute then, break it out of the person it's in. So if you multiply this out, so there's your y prime there when I multiply that out. As for the other one, you can kind of take the same approach, I suppose. You want to separate the y primes from the guys that are non-y primes. Yeah, so I just took this guy, I multiplied out. E to the x plus y squared times 1, I get that. And then e to the x plus y squared times 2y, y prime, I get that. Can move everyone without the y prime to the other side. So I would have, well, on this side, I would have y prime times 2y e to the x plus y squared plus 1 over x plus y equals minus e to the x plus y squared minus 1 over x plus y. So this means that my y prime is going to be minus e to the x plus y squared and then this minus everything here divided by 2y e to the x plus y squared plus 1 over x plus y. And of course, can simplify this a little bit by multiplying by x plus y over x plus y. And we have that. That's that one. Okay. So now let's look at the second example. We want to find the VDP, assuming that that equation is true. Does anyone recognize that equation? It's probably something I wanted to ask. Look familiar? Something you might have seen somewhere? So here, maybe this will help. P represents pressure, and V represents volume. Does that strike a bell? I don't know. I don't really know what other classes you guys have taken already, but this is actually an expression from chemistry. So it's not just a randomly made up example. It's like an actual thing. It's like an actual expression, actual equation. This is called van der Waals equation. It's not two A's. It's two A's in the other thing. This is called van der Waals equation for a specific gas. So it's a thing in chemistry, and so I just wanted to kind of give a somewhat real world example, like not just something I just made up, but something that actually comes from someone studying something in the real world in science, and they come up with a relationship where the two things that they care about, pressure and volume, are kind of commingled up together. So the importance, not only does implicit differentiation help us with situations where, as we did last time, where I couldn't solve for the function, I didn't know what the function is, but I still could describe the slope of a tangent line to the curve of the function, and the benefits of being able to do that. But sometimes implicit differentiation is important because when you discover some sort of relationship in the real world, sometimes it comes to you in implicit form. You just know that the variables mix together to make this happen, right? You can't really isolate one in terms of the other, but you know that if you mix things in a certain way, this is the result, right? And so I just wanted to give you an example of that. So this is van der Waals equation for a specific gas. And at the end of the day, I want to know dV dP. In other words, if I were to change the pressure of the gas, how fast would the volume change in response, right? So if I change the pressure from, like 1 atmosphere to 2 atmospheres, how fast does the volume respond? How much does the volume change in that? Does it change like a huge amount? Is it like an explosion? That wouldn't be great. Or is it something else, right? So this is the kind of question that we'd want to be able to ask. How fast does volume change in relation to pressure? As my pressure is increasing by 1 atmosphere per second, how much is my volume increasing in centimeters cubed per second or something like that? So that's what we ultimately want to find. So now I can kind of rewrite this as, so we have P plus 5V to the minus 2 times V minus 0.03 equals 9.7. So if I go through and started differentiating this, how would I actually do that?
One minus 10 over V to the 3V prime, the first.
Okay, so the derivative of P with respect to P is just 1. The P is like the independent variable here. So yeah, you have derivative of that is 1 plus the derivative of this is going to be, well, minus, 10 V to the minus 3 V prime, because the V prime is the guy you want, right? So you know that here, the P is the independent variable. So that's the guy you can just differentiate and not worry about it. The V is the dependent variable, which means you need to multiply by V prime whenever you differentiate. Okay. So, and then what? Now what? So would I just multiply this by say V prime minus 0? Yeah. And then I get equal to 0.
Is the product rule?
Right. No, that would be illegal what I just did. So no, because I just violated the product rule. Remember, just because we're in implicit differentiation doesn't mean all the other calculus rules get thrown out the window. We need a product rule here. So here, how do you like undo this thing? So here, finally, I have two functions like f and g. So we need the product rule. Now I could multiply this out, but I would still end up with a p times a v, which I would need the product rule anyway. So might as well just use it now. But the product rule is still a thing. So I differentiate one term, leave the second term, plus now I leave the first term, differentiate the second term. Right? All the rules, the old derivative rules are still a thing. Okay, so now I'm up in a situation where I want to find v prime, want to find dv dt. So this means I am going to want to kind of break this out of prison here. So I'd expand, this is v minus 0.03 minus 10v to the minus 2v prime minus 0.3 v to the minus 3v prime plus tv prime plus 5v to the minus 2v prime. So I just took the one, multiplied everyone in the second pair of parentheses. Then I took the minus 10, that should be a plus, the minus 10v to the minus 3 v prime, multiply everyone in the second parentheses. So I get v to the minus 3 times v gives me v to the minus 2. So that's where this term comes from. And then I took 10 v to the minus 3 v prime times the minus 0.03. And that's where this term comes from. Because multiplying by 10 just moves the decimal point one place to the right. Then I just multiply out the v prime into the other guy. So we have that. Now I just want to isolate my v prime. What do I have here? I have 10v to the minus 2. That takes care of that guy. I also have plus 0.3v to the minus 3. That takes care of that guy. Plus p. That takes care of that guy. Plus 5v to the minus 2. And that takes care of that guy. Which, by the way, I can actually combine some of these. So this is, and on that side, I would move the other guy. So this is 0.03 minus b. And that moves this guy over, moves that guy over. Okay, everyone's accounted for. Here, I have minus 10v to the minus 2 plus 5v to the minus 2. So that's really minus 5v to the minus 2. So I can think of this as p plus 0.3v to the minus 3 minus 5v to the minus 2. And so my dv dt is equal to 0.03 minus v over p plus 0.3v to the minus 3 minus 5v to the minus 2. And that's the guy. It's coming in here. All right. So even if you don't have x's and y's, don't be confused. Remember, the intuition behind implicit differentiation is you differentiate as usual. You have to remember all your derivative rules. Product rule, still a thing. You cannot violate it. Chain rule, still a thing. You cannot violate it. Quotient rule, all of that, still things, right? So don't forget them. In this case, we needed the product rule. But the important thing is, on top of that, once you identify who the independent variable is, when you apply the derivative rules I gave you, you don't really have to do anything. You just kind of apply them, pretending that the guy is an x. But if you differentiate anyone else, anyone who's not the independent variable, any letter that's not that guy, you have to multiply by its prime. And that's because of the chain rule that we've been discussing last time. So that's what that guy would look like. Okay, so to motivate the next section, let's find the derivative of x to the x. So this is our focus for a little bit. What do you think the derivative of that function is? Give me a guess. X raised to the x power? What do we do? Let me tell you what not to do. Here are two common things that would happen, especially if I put this on a test. And it's so common that even sometimes after I talk about this in class, it still happens on a test. Yeah, it's one of those things. But here's some common incorrect guess. Steele would think, I can just use the power rule, right? I mean, it's the derivative of x to a power. So I can bring that power down and then subtract 1 from the power, right? But that is incorrect. But why is that incorrect? So that they would think use the power rule. Why is this incorrect? Which is very important. I mean, what is the power rule? What does that say? What does the power rule say? If you were to state the power rule, what would you say? You guys forgot the power rule? Can't forget the power rule. Power rule is like super important. It starts out with d dx of x to the n equals what does that equal according to the power rule?
Isn't it n x to n minus 1?
That's right. That's the power rule, right? So that's it, right? Now, here's the important thing. So remember, I said knowing your rules super important. So the moment I asked the power rule, you should have been able to immediately say it. So it's actually not a good sign that there was such a long pause. So let's go beyond that now, though. You need to know your rules. You need to know them exactly. You need to know them right away. Otherwise, this class is just going to be way harder than it has to be. So that's the first thing. The second thing, though, is because the rules are your templates, like I said, they tell you what you're allowed to do, how you're allowed to manipulate things. You have to understand what the pieces of those rules are. So here, and this is the important thing to also know, you have to know what the things in the rules are. So your x is what here? Well, it's your independent variable. Now, what is the n here in this rule? What does the n represent in this rule?
a constant?
It's a
Or
constant. Right? Which means I'm allowed to use this rule when my power is a constant. If I look at this, is that the case? No, it is not. The power is also a variable, which means you applying this rule means either you didn't know the power rule correctly and you kind of did something on instinct, or you knew the power rule, but you didn't really pay attention to what the individual pieces in the power rule was. And so you're like, well, anything to a power, just move the power down and subtract 1, right? No, you can only do that if the thing in the power is a constant and the base is the independent variable, right? So that's the power rule. It's actually very important that you not actually only know the rule, but also know how the rule is applied. What are the things in the rule? So this is a very common guess, but it's an incorrect guess. And this is an incorrect guess because students don't really pay attention to what the power rule is. Now, another common guess I get sometimes not as common as the first one, semi-common, also incorrect guess. Is to think that d dx of a to the x, well, I know a rule that says d dx of a to the x. So I remember a rule where there was an x in the power, and the derivative of that was a to the x ln a. So maybe the derivative of this is x to the x ln x. Maybe that's going to be what it is, right? Trying to apply this erroneously. And again, why is that? Here, your x is the independent variable. And what is your a? Your a is a positive constant. Positive constant, that's not equal to 1. Although it could also equal 1, but we normally think of it as greater than 1 or something. Just 1. It could be 1. It's just that if it was 1, we would just think of the function as 1, and we know that the derivative of 1 is 0. But you'd still get that here because if you take the log of 1, you get 0. But it's kind of weird. We usually don't think of it as 1. But it definitely is positive because we need it to work inside the ln. But it's a positive constant, not just any constant, right? Which means if I look at this, the x to the x also does not apply here. This rule does not apply because the base here is not a constant. The base is not a positive constant. So both of these rules would not apply. So this guy is a little bit trickier than meets the eye at first. So to deal with the derivative of x to the x gets tricky. The easiest thing would be if the power were constant, we can apply the power rule and get on with our lives. But it's not, of course. So the power being a variable at the same time as the base is an issue. Okay, so now I'm going to follow up with another question. One that I hope, because I ranted on this for just a little bit, not for too long, for just about a minute. So maybe let's see if we actually learned and sink in, how do we deal with this issue? So you look at something and you're like, the power is an issue. I mean, if it was a constant, I'd be great, but it's not, right? So the power is a problem. How do we deal with it when powers are problems? What do you think? What is your go-to weapon?
Logs.
Logs, logarithms, right? Right? Remember, this is the inverse operation. You want to get rid of a power. You want a power to not be a problem anymore, right? You send in the logs, right? Same way, if something's being added, you want it to not be adding anymore, you send in subtraction. You have a multiplication, you want there not to be a multiplication anymore, you send in division. The same way, you're raising something to a power, you want something not raised to a power anymore, you send in a logarithm. This is the concept, right? And I kind of try to hammer that home. Logs cancel powers, powers cancel logs, they undo each other. If one is an issue, use the other one. If you have a logarithm, you don't want it there, exponentiate. If you have an exponential and you don't want it there, log it, right? So that's what we're going to do. So here's how we can actually do this. So set y equals x to the x. I want to find y prime. What I can do is the power x is a problem. So what I'm going to do is I'm going to log both sides. Now what I can do is stop the power from being a problem. Having the log there allows me to bring that power down into a multiple, into a product. And I happen to know how to differentiate products. This is no longer an issue. We have the product rule. So this means I can differentiate both sides. Derivative of ln y is y prime over y using our rules. Derivative of this side is you differentiate one thing, leave the other thing, plus you leave one thing, differentiate the other thing. That is product rule. In other words, this means that y prime over y is equal to ln x plus 1. This means that my y prime is equal to y times ln x plus 1. But my y is what? My y is x to the x. So yeah, that's the derivative. In other words, the derivative of x to the x is x to the x times ln of x plus 1. Now, that's not a rule that you have to memorize, but the process that I use to get to this is what's important. And you might also recognize that this is the same process I actually used to derive the power rule for you. It was exactly the same process. Again, when the power rule, remember why we did logs when I was deriving the power rule, because the power was a problem, right? If your n was a power 1,000, you don't want to have to multiply all that out when you're doing the f of x plus h minus f of x over h. So we're like, I don't want the power to be a problem anymore. Log both sides. And we found that, you use the constant factor rule in this step instead of the product rule, because your n was in front and it was just a constant. And you figured out the power rule that way. So we can do that there. Now, what I did not tell you at the time was that what I was doing was actually a method. And that method is the next section, right? The above process involving implicit differentiation, of course, because you see I had differentiated a y term I had to multiply by a y prime. So it involves implicit differentiation, but it's geared towards a very special idea. It involves implicit differentiation. Now, the time when I was deriving this, I told you it involved the chain rule, but now we know that implicit differentiation is really just an application of the chain rule. So I still wasn't leading you astray back then. Involving implicit differentiation is called log differentiation. It's when you introduce a logarithm to make your derivative easier. So here is the process. So suppose we have y equals f of x, and we want y prime. One way to get this, and I'm going to tell you when you might want to try something like this as well, is to one, log both sides, right? To get ln of y equals ln of f of x. Two, simplify the right side using log rules. So obviously, the logs help with certain things, right? They turn powers into multiples. They turn multiplication into sums. They turn division into subtraction, right? So you can have something that's very complicated computationally with a lot of powers and multiplications and divisions and stuff, but you can turn these all into multiplications, sums, and subtractions, right? So you are allowed to do that. And the idea is using the log can help you differentiate something easier. So this is also something I believe we saw last time, the time before that, when we had, you can have something complicated like we had right here, but with a log in front of it, it just becomes not complicated anymore. You can use the log to break it down into simpler terms, right? So that's what this is about. Then three, you would differentiate implicitly. Because step two makes it easier to differentiate. So now you just differentiate. And then four, you solve for y prime, which usually involves just multiplying both sides by the original y, and the original y you would actually know. When is this useful? Why would someone think about doing this? Couple situations. One, powers are a problem. So we can use logs to get rid of them. So I should say when powers are a problem. So when powers are a problem, we can use logs to get rid of them. That's one thing. So in particular, when base and power have variables in them, as we just saw. Because if the power has no variable in it and it's a constant, it means you can apply the power rule. If the base has no variables in it and it's just a constant, it means you can apply the a to the x rule. If both have variables in it, neither of those rules apply anymore. So you would start to think log differentiation. Another situation which might be surprising is this situation. The product and or quotient rule would be very annoying to apply. Again, going back to 2 sessions ago, to actually differentiate the cube root of that monstrosity, you'd have to apply the chain rule, then multiply by the derivative of the inside, which you're applying a quotient rule, which while you're doing that, you have to do the product rule, which while you're doing that, you have to do the chain rule. It gets really messy really fast, right? To differentiate what's in that blue circle, it would be really annoying to go directly by quotient rule and product rule and all that stuff, right? Whenever you're in that situation where you're like, that's going to be hella annoying to actually do with the product and quotient rule, log differentiation should come to your mind right away, right? And we are going to do some examples. So let's do some examples. So one, let's say I want to differentiate the cube root. Let's look at a similar one, x to the 7 e to the 3x over x plus 1 to the 4, and b, differentiate e to the x squared plus x to the x squared. I want to get through both of these, but we lost too much time on technical difficulties. So I'll do one, you do the next one, and we can pick up on Friday with that and then move on to something pretty cool. So next class, I actually want to talk about something called l'Hopital's rule. Said that in a French accent for a very specific reason. Yeah, so what we can do here is set y equals the cube root of x to the 7 e to the 3x over x plus 1 to the 4th. Then what I can do is I can log both sides. The log allows me to simplify the right side. It will become 1/3 times 7 ln x plus 3x minus 4 ln of x plus 1. Now, each of those individually is really easy to differentiate. So now when I differentiate implicitly, derivative of that is 7 over x, derivative of this is 3, derivative of this is 4 over x plus 1. And so now my y prime is going to be this. Now I challenge you to actually do this directly. You can try that and tell me how you feel about it on Friday as well. So here I have 1/3 times the cube root of the original. So this is the original function, x to the 7th e to the 3x over x plus 1 to the 4 times 7 over x plus 3 minus 4 over x plus 1. That's our y prime, which it looks like a monstrosity, but it was actually, I think psychologically, you know, it was easy to actually get there, which it would not have been had you try to do the chain rule, then multiply by the derivative of the inside, which you have to do the product rule within the quotient rule and a chain rule within the quotient rule. It would have been really annoying, but that was actually pretty okay. We'll stop there. I'll give you a variation on log rules, like a variation on the method next time, as well as going into l'Hopital's rule. But for now, we will end there. So hopefully that was clear. Thank you for your time and attention. I'll leave that other example in the notes, but it was to differentiate e to the x squared plus x to the x squared. Think about it. Try to figure out how to use logs to do it. And yeah, I will pick up with that next time. So see you guys on the next one. Ciao.